The year was 1901. Guglielmo Marconi stood on a clifftop in Cornwall, England, adjusting his primitive radio receiver. 3 simple dots crackled through the static. The letter S in Morse code, transmitted from across the Atlantic Ocean. It was humanity's first successful transatlantic radio communication. Marconi had no idea he'd just fired the opening shot in a conversation that would echo across the galaxy. Today, 123 years later, that single radio pulse has become a flood. Every baseball game broadcast echoing into the void. Every television signal carrying our hopes, dreams, and advertisements to distant stars. Every military radar scanning our skies, inadvertently announcing our presence to cosmic neighbors we've never met. We've been shouting into the dark for over a century, creating an expanding bubble of human chatter that now stretches 130 light-years from Earth. But here's what keeps astronomers awake at night. Starting in 2017, mysterious objects began visiting our solar system with unprecedented frequency. Oumuamua, 2I/Borisov, 3I/Atlas, each one stranger than the last. What if our century of electromagnetic noise finally reached a listener? What if these aren't random cosmic debris, but the universe's way of saying, "Message received"? Tonight, we trace humanity's journey from accidental cosmic broadcasters to intentional interstellar messengers. We'll explore the profound implications of our expanding radio bubble, the deliberate attempts to reach out across the void, and the unsettling possibility that someone or something might finally be responding to our calls. The story begins not with grand scientific ambitions, but with the simple desire to hear a baseball game. Picture America in the 1920s. Radio was the internet of its age, connecting isolated communities across vast distances. Families gathered around crystal sets to hear the latest jazz from Chicago, news from New York, and yes, play-by-play coverage of the World Series. But radio waves don't stop at the horizon. They keep traveling, growing weaker but never truly dying, racing outward at 186,000 miles per second. Dr. Frank Drake, pioneer of the search for extraterrestrial intelligence, puts it perfectly. Every radio transmission we've ever made is still out there, traveling through space. Somewhere 50 light-years away, alien civilizations might be listening to the 1974 World Series. Think about that. The dramatic bottom-of-the-ninth homer that won the Oakland Athletics the championship is now a faint whisper passing through star systems we can barely see with our most powerful telescopes. Those victory celebrations, the crowd's roar, the announcer's breathless commentary, all of it preserved in radio waves, carrying human emotion across the cosmic void. But it wasn't just entertainment bleeding into space. The real cosmic commotion began during World War II when humanity developed radar. Suddenly, we weren't just passively broadcasting, we were actively pinging the universe with powerful radio pulses designed to detect enemy aircraft. The first operational radar systems, like Britain's chain home network, pumped out millions of watts of radio energy. For the first time in Earth's 4.5 billion year history, our planet became artificially bright in radio wavelengths. Any technologically advanced civilization monitoring radio frequencies would have noticed this dramatic change almost immediately. Dr. Jill Tarter, former director of SETI Research, describes the moment. Around 1945, Earth suddenly became much more detectable. Our radio signature went from essentially zero to blazing across multiple frequencies. From a cosmic perspective, it was like someone suddenly turning on a lighthouse. Consider the timeline. Those first radar pulses, transmitted between 1940 and 1945, have now traveled between 78 and 83 light-years from Earth. That bubble encompasses roughly 20,000 star systems, including several with confirmed exoplanets. Any civilization within that expanding sphere would have detected our transition from radio quiet to radioactive. The implications stagger the imagination. Within a few decades of inventing radar, we transformed Earth from an electromagnetically invisible world to one of the brightest radio sources in our local galactic neighborhood. We announced our technological presence to thousands of star systems without even realizing we were doing it. Television broadcasting added another layer to our cosmic signature. Beginning in the late 1940s, TV stations began pumping powerful VHF and UHF signals skyward. The early broadcasts were crude by today's standards: black and white images of variety shows, news broadcasts, and primitive dramas. But to any alien intelligence monitoring Earth, they would have represented something extraordinary: organized, structured electromagnetic signals carrying complex information. The content of these early TV broadcasts has become the stuff of legend among SETI researchers. The 1953 coronation of Queen Elizabeth II was one of the first major global television events, watched by an estimated 277 million people worldwide. Those television signals, carrying images of British royalty and ceremonial pageantry, are now racing past stars like Wolf 359 and Ross 128, potentially providing alien civilizations with their first glimpse of human culture and social organization. Even more intriguing are the unintentional messages embedded in our entertainment. The 1960s sitcom The Andy Griffith Show, with its portrayal of small-town American life, has been broadcasting human values and social relationships to nearby star systems for over 6 decades. The show's theme song, that gentle whistling melody, might be humanity's most widely distributed cultural artifact, carried on radio waves to hundreds of solar systems. But television wasn't our only contribution to the cosmic conversation. The development of planetary radar in the 1960s created some of the most powerful radio transmissions in human history. When NASA's Arecibo Observatory bounced radar signals off Venus to map its surface, those transmissions briefly made Earth the brightest radio object in our local stellar neighborhood. Dr. Stephen Ostro, who pioneered planetary radar astronomy, explained the significance. When we illuminate Venus or an asteroid with radar, we're transmitting millions of watts in a highly focused beam. For those few minutes, we're essentially creating a radio beacon visible across hundreds of light years. These radar astronomy sessions created brief but intense radio signatures that would stand out dramatically against Earth's normal electromagnetic background. Any monitoring civilization would detect these transmissions as clearly artificial, too powerful, too focused, and too precisely timed to be natural phenomena. The cumulative effect of all this activity has created what astronomers call our radio bubble, an expanding sphere of electromagnetic energy centered on Earth and growing at the speed of light. This bubble now encompasses roughly 15,000 cubic light years of space, containing an estimated 75,000 star systems. But here's where the story becomes truly fascinating. The character of our radio emissions has been changing. In recent decades, we've become more efficient at containing our signals. Satellite communications, fiber optic cables, and digital broadcasting have reduced the amount of energy we leak into space. From an alien perspective, Earth's radio signature peaked sometime in the 1980s and has been gradually dimming ever since. Dr. David Messerschmidt from UC Berkeley notes, "We're in a unique window of technological development. For about 50 years, from 1950 to 2000, we were incredibly bright in radio wavelengths. Now we're starting to go quiet again. Any alien civilization would see this as a fascinating evolutionary pattern." This raises a profound question. If alien civilizations follow similar technological development patterns, there might be brief windows when they're detectable before they transition to more efficient, less leaky communication technologies. We might be living through the exact period when multiple civilizations throughout our region of the galaxy are visible to each other for the first time. The mathematics of our expanding radio bubble reveal both the enormity and the limitation of our cosmic presence. At 130 light-years from Earth, our strongest early television signals have weakened to roughly 1/1000th of their original strength. They're still detectable with sufficiently sensitive equipment, but alien civilizations would need technology comparable to our largest radio telescopes to distinguish our signals from natural cosmic background noise. Yet even these faint whispers carry unmistakable signatures of intelligence. The structured nature of television broadcasts, with their regular timing, consistent frequencies, and information content, would stand out clearly against the random noise produced by natural astronomical phenomena. An alien SETI program monitoring our region of space would have no difficulty identifying these signals as artificial in origin. The content flowing outward in our radio bubble creates an unintentional time capsule of human civilization. The 1960s moon landing broadcasts, carrying Neil Armstrong's first words from the lunar surface, are now approaching stars like Altair and Vega. The 1969 Woodstock Festival, with its messages of peace and music, races toward the constellation Lyra. The fall of the Berlin Wall in 1989 propagates toward distant suns, carrying humanity's joy at the end of the Cold War. But our cosmic conversation hasn't been entirely accidental. Starting in the 1970s, humanity began making deliberate attempts to communicate with potential alien civilizations. These efforts represented a fundamental shift from inadvertent broadcasting to intentional messaging, from cosmic noise to cosmic diplomacy. The first serious attempt came in 1972 and 1973, when NASA launched Pioneer 10 and 11 with identical golden plaques attached to their spacecraft. These plaques, designed by Carl Sagan and Frank Drake with artwork by Linda Salzman Sagan, represented humanity's first deliberate message to the cosmos. The Pioneer plaques were masterpieces of universal communication design. They showed the hyperfine transition of hydrogen, the most abundant element in the universe, providing a universal unit of time and distance. They mapped our solar system, indicating Earth as the third planet from a medium-sized star. Most boldly, they included line drawings of a nude man and woman standing beside the spacecraft for scale, their hands raised in greeting. Dr. Linda Salzman Sagan, who created the artwork, recalls, "We wanted to show who we were and where we came from." The naked figures were controversial. Some people thought it was inappropriate to send nudity to aliens. But we felt that showing the human form honestly was essential for any meaningful communication. The plaques included a radial map showing the position of our sun relative to 14 nearby pulsars, cosmic lighthouses whose precise timing could help alien recipients locate Earth even millions of years in the future. This stellar GPS system represented a remarkable leap of faith, the assumption that any civilization advanced enough to intercept our spacecraft would possess the astronomical knowledge to decode our cosmic address. Pioneer 10 and 11 are now beyond the heliopause, in genuine interstellar space, carrying their golden messages toward distant encounters that may not occur for millions of years. Pioneer 10 is heading toward the constellation Taurus, while Pioneer 11 travels toward Aquila. These silent ambassadors represent humanity's first physical messages to the galaxy, traveling far slower than radio waves but destined to survive long after our electromagnetic signals have faded below detectability. But NASA wasn't finished with interstellar messaging. In 1977, the Voyager 1 and 2 missions carried a more ambitious attempt at cosmic communication, the Golden Records. These 12-inch copper phonograph records, plated with gold for longevity, contained a far more comprehensive portrait of human civilization. Carl Sagan, who chaired the committee that created the record's content, called it a message to the universe and a gift to the cosmos. The Golden Records included 116 images showing the diversity of life and culture on Earth. Mathematical and physical definitions provided universal context. Images of human anatomy, conception, and birth illustrated our biological nature. Family groups, architecture, art, and music demonstrated our social and cultural achievements. But perhaps most remarkably, the records contained 90 minutes of music from around the world. Bach's Brandenburg Concerto No. 2, Chuck Berry's Johnny B. Good, traditional songs from various cultures and sounds of Earth including whale songs, thunder, and a human heartbeat. Ann Druyan, creative director of the Golden Record Project, describes the selection process. We tried to create a portrait of Earth that would be meaningful to any intelligence that might encounter it. The music was especially important. We felt that melody and rhythm might be truly universal languages. The inclusion of Chuck Berry's rock and roll classic sparked considerable debate. Some scientists questioned whether popular music adequately represented human culture, while others worried about the message sent by Berry's energetic guitar riffs and lyrics about American teenagers. But the committee felt that the song's exuberance and mathematical precision of its musical structure made it an ideal ambassador for human creativity. The Golden Records also included greetings in 55 languages, from ancient Sumerian to modern Mandarin. Each greeting was brief and peaceful. Hello from the children of planet Earth, spoken in dozens of human tongues. These linguistic samples provided potential alien recipients with evidence of our cultural diversity, while demonstrating the fundamental similarity of human communication across different societies. But the most focused and powerful deliberate message came from the Arecibo Observatory in Puerto Rico on November 16, 1974. The Arecibo message, as it became known, represented humanity's first serious attempt at interstellar radio communication. Dr. Frank Drake, who conceived and designed the message, worked with a team of scientists to create exactly 1,679 bits of binary information. The number wasn't arbitrary. 1,679 is the product of two prime numbers, 23 and 73. Any mathematically sophisticated civilization receiving the message would recognize this hint and arrange the bits into a rectangular grid of 23 columns by 73 rows. When properly arranged, the binary pattern would reveal itself as a pixelated diagram containing several key pieces of information about humanity and Earth. The top section showed our number system, counting from 1 to 10 in binary. Below that, atomic numbers identified the chemical elements essential to life: hydrogen, carbon, nitrogen, oxygen, and phosphorus. The middle section depicted the double helix structure of DNA and provided the approximate number of nucleotides in human genetic material. A crude stick figure represented the human form, with a number indicating the average height of an adult human in terms of the message's basic unit of measurement, the wavelength of the transmitted radio signal. The bottom portion showed our solar system, with the third planet offset from its orbital line to indicate Earth as the source of the message. Finally, a diagram of the Arecibo telescope itself demonstrated the technology used to transmit the signal. The transmission lasted exactly 169 seconds, less than 3 minutes, and used Arecibo's maximum power output of nearly 1 million watts. For those brief moments, the giant dish became the brightest radio source in our local galactic neighborhood, blazing across the cosmos with focused intensity. The target was M13, the Great Globular Cluster in Hercules, chosen because it contained roughly 400,000 stars, packed into a relatively small region of space. The cluster is approximately 25,000 light-years from Earth, meaning our message won't arrive until around the year 27,000 CE. By that time, human civilization as we know it will likely have transformed beyond recognition, or vanished entirely. Dr. Drake acknowledges the ceremonial nature of the transmission. We knew M13 was too far away for any practical communication, but we wanted to demonstrate that interstellar messaging was technically feasible. It was a proof of concept, not a serious attempt at conversation. Yet the Arecibo message represented something profound, humanity's first deliberate shout across the cosmos, our initial attempt to announce ourselves as an intelligent, technological species capable of reaching across the vast distances between stars. The message sparked immediate controversy. Some scientists worried about the wisdom of advertising our location to potentially hostile alien civilizations, Others criticized the content, arguing that the stick figure representation of humans was too crude and the mathematical concepts too elementary for any truly advanced intelligence. But supporters of the project saw it differently. Carl Sagan argued that any civilization capable of receiving and decoding our message would necessarily be more advanced than us, making them more likely to be benevolent explorers than cosmic conquerors. The act of transmission, he believed, said more about humanity than about our intended recipients. The scientific rationale for radio communication as the preferred medium for interstellar contact had been established 15 years earlier. In 1959, physicists Giuseppe Cocconi and Philip Morrison published a landmark paper in the journal Nature, titled Searching for Interstellar Communications. Cocconi and Morrison argued that radio waves represented the logical choice for interstellar messaging because they travel at the speed of light, penetrate interstellar dust and gas with minimal attenuation, and require relatively modest energy expenditures compared to other forms of electromagnetic radiation. They specifically identified the 21-centimeter wavelength of neutral hydrogen as a promising frequency for interstellar communication. This wavelength corresponds to a quantum mechanical transition in hydrogen atoms and would be universally known to any technologically advanced civilization, providing a natural meeting point in the electromagnetic spectrum. The paper concluded with a prescient observation. The probability of success is difficult to estimate, but if we never search, the chance of success is zero. This logic launched the modern search for extraterrestrial intelligence, transforming interstellar communication from science fiction speculation to serious scientific endeavor. Radio telescopes around the world began systematic searches for artificial signals from space, while scientists developed increasingly sophisticated techniques for distinguishing natural cosmic noise from intentional transmissions. But as our radio bubble expanded and our deliberate messages raced toward distant stars, humanity began to grapple with a fundamental question. What if someone was already listening? What if our century of electromagnetic chatter had already been detected, analyzed, and understood by intelligences we couldn't yet perceive? The first hints that our cosmic monologue might be becoming a dialogue arrived in 2017, when astronomers detected something unprecedented racing through our solar system. An object so unusual that it challenged every assumption about comets, asteroids, and the nature of interstellar space. They named it Oumuamua, Hawaiian for messenger from afar arriving first. But as we'll discover in our next chapter, this mysterious visitor might have been carrying messages of its own, responses to a century of human signals finally reaching their intended recipients. The expanding bubble of our radio transmissions had reached thousands of star systems. Our deliberate messages were racing toward their cosmic destinations. And now, something was coming back. The conversation was about to become a lot more interesting. But first, we needed to understand where to listen and where to speak. In their groundbreaking 1959 paper, physicists Giuseppe Cocconi and Philip Morrison didn't just argue for radio communication, they identified the perfect cosmic meeting place. They pointed to the water hole, that remarkably quiet region of the electromagnetic spectrum between 1.42 and 1.66 gigahertz, bounded by the emission lines of hydrogen and the hydroxyl radical OH, the building blocks of water itself. This wasn't arbitrary. Any civilization that understood basic chemistry would recognize the profound significance of this spectral neighborhood. Here, in the frequencies that bracket the most essential molecule for life as we know it, the galaxy falls naturally silent. Cosmic background noise drops to its minimum levels, creating a natural communication channel carved out by the universe itself. Dr. Bernard Oliver, who helped define the waterhole concept at NASA's Ames Research Center, explained the logic. If you're planning a cosmic cocktail party, you meet at the waterhole. It's where everyone who understands chemistry would naturally think to look. The hydrogen line at 1420.4 MHz became particularly significant, a frequency that represents one of the universe's most fundamental processes. This emission occurs when a hydrogen atom's electron flips from parallel to anti-parallel alignment with the proton's magnetic field. It's the most abundant element in the universe undergoing its most basic quantum transition. The mathematics are elegant in their simplicity. Every hydrogen atom in the cosmos occasionally undergoes this spin-flip transition, releasing a photon at precisely 1420.4 MHz. The frequency is as universal as the speed of light, as fundamental as gravity. If aliens wanted to establish a cosmic communication standard, hydrogen's signature would be the obvious choice. Our own searches have followed this reasoning for decades, with mixed results and growing sophistication. The SETI Institute's receivers have been scanning the hydrogen line since the 1960s, accumulating hundreds of thousands of hours of observation time. The Breakthrough Listen project, funded by technology billionaire Yuri Milner, monitors millions of stars across multiple frequencies simultaneously, processing data at rates that would have been unimaginable just a generation ago. The Allen Telescope Array in Northern California represents the cutting edge of this effort. 42 radio dishes working in perfect synchronization, capable of observing multiple star systems simultaneously while automatically rejecting interference from human technology. When completed, it will consist of 350 dishes, creating one of the most sensitive SETI instruments ever constructed. But decades of searching the waterhole have yielded something unexpected: profound silence. The cosmic quiet we hoped would carry alien voices has remained stubbornly empty of artificial signals. This silence has forced us to confront uncomfortable questions about our assumptions, our methods, and perhaps our expectations. The challenge becomes clear when we examine our own electromagnetic signature from an alien perspective. Most of our television and radio signals, once they escape Earth's atmosphere, become indistinguishable from background noise within just a few light years. The inverse square law governing electromagnetic radiation is utterly unforgiving. Double the distance, quarter the signal strength. Dr. Seth Shostak from the SETI Institute puts it bluntly: our sitcoms and baseball games might not be making it to Alpha Centauri in detectable form. The universe is a much quieter place than most people imagine. Only our most powerful transmissions survive the journey to nearby stars, with enough intensity to be detected by alien technology comparable to our own. Planetary radar systems like Arecibo's S-band transmitter or the Goldstone Deep Space Network's X-band array represent humanity's brightest radio beacons, shining with enough intensity to be detected across dozens of light years. These systems, originally designed to map asteroids and planets, accidentally serve as cosmic lighthouses. Their beams sweep across the cosmos every time Earth rotates, creating distinctive signatures that would be unmistakable to any civilization monitoring our region of space. The radar pulses are brief but incredibly intense. For those few seconds when a beam passes through an alien radio telescope, Earth would appear as one of the brightest radio sources in the local galaxy. The Deep Space Network represents humanity's most sophisticated attempt at cosmic communication infrastructure, though it wasn't designed for that purpose. 3 massive antenna complexes in California's Mojave Desert near Madrid, Spain, and outside Canberra, Australia, maintain continuous contact with our robotic explorers scattered throughout the solar system. These installations house some of the most sensitive radio equipment on Earth. The largest dishes stretch 70 meters across, their surfaces crafted to tolerances measured in millimeters. To an alien radio telescope, our Deep Space Network signals would create a distinctive pattern: narrow carriers appearing and disappearing as our planet rotates, structured emissions clustered around a small blue world that seems unusually active in the radio spectrum. Dr. Douglas Vakoch, former director of interstellar message composition at the SETI Institute, describes what aliens might observe. Our spectrum would look peculiar, compared to natural astronomical objects. The structured emissions of FM radio and television, each channel occupying its designated frequency slot. Brief, intense radar pulses sweeping across the sky in regular patterns, all of it clustered around one small planet that's clearly doing something very unusual. The International Telecommunication Union, headquartered in Geneva, coordinates global spectrum allocation, ensuring that radio services don't interfere with each other. They've designated specific frequencies for radio astronomy, recognizing that some bands must remain clear for us to hear the universe. These protected frequencies represent windows of artificial silence in our increasingly noisy electromagnetic environment. Radio quiet zones around major observatories restrict terrestrial transmissions that might interfere with sensitive receivers. The National Radio Quiet Zone in West Virginia spans 13,000 square miles, creating an oasis of electromagnetic silence around the Green Bank Observatory. Within this zone, cell phones are banned, microwave ovens are restricted, and even automotive ignition systems must meet special requirements to prevent interference with astronomical observations. But here's what's truly remarkable. Despite all these efforts to create artificial silence for listening, we've heard nothing that definitively indicates artificial origin from beyond our solar system. The cosmic water hole remains as quiet as a tomb, its silence growing more profound with each passing year of fruitless observation. This silence has split the SETI community into two philosophical camps, each with radically different approaches to the challenge of interstellar communication. Traditional SETI has always been about passive listening, the assumption that alien civilizations are already broadcasting, and we need only build sensitive enough receivers to hear them. The Breakthrough Listen project processes petabytes of data from radio telescopes worldwide, searching for patterns that don't belong in nature's chaotic symphony. Their algorithms can identify artificial signals buried in cosmic noise, distinguish between natural and artificial emissions, and automatically reject interference from human technology. The SETI Institute operates multiple programs under this passive paradigm. The Allen Telescope Array scans thousands of star systems simultaneously, while optical SETI searches for powerful laser pulses that might serve as interstellar beacons. The assumption underlying all these efforts is that someone, somewhere, is deliberately trying to get our attention. But there's another camp, one that questions whether passive listening is sufficient. Active SETI, sometimes called METI, Messaging Extraterrestrial Intelligence, argues that we should be transmitting as well as receiving. If every civilization in the galaxy is sitting quietly, waiting to hear from someone else, the result would be cosmic silence despite the presence of numerous technological species. Dr. Douglas Vakosh, who became one of the leading advocates for active SETI, frames the dilemma. Imagine a cocktail party where everyone is too polite to speak first. The room could be filled with fascinating people, but you'd never know it if everyone's waiting for someone else to break the ice. The philosophical divide runs deeper than mere strategy. Passive SETI assumes that alien civilizations are already broadcasting, either deliberately or accidentally, and that our role is simply to detect these existing signals. Active SETI assumes that advanced civilizations might have evolved beyond the need for wasteful, omnidirectional broadcasting, requiring us to initiate contact if we hope to establish communication. The technical challenges facing both approaches are formidable. For passive SETI, the problem is sensitivity and processing power. Radio signals from distant civilizations would be incredibly weak by the time they reach Earth, requiring enormous dish antennas and sophisticated signal processing to detect. The Square Kilometre Array, currently under construction in Australia and South Africa, will provide unprecedented sensitivity when completed, capable of detecting signals from Earth-like transmitters around nearby stars. For active SETI, the challenge is power and targeting. Transmitting a signal strong enough to be detected across interstellar distances requires enormous amounts of energy. The Arecibo message used nearly 1 million watts for just 3 minutes. A continuous beacon visible to nearby civilizations would demand power outputs comparable to small cities, raising questions about resource allocation and environmental impact. The targeting problem is equally complex. With hundreds of billions of stars in our galaxy alone, where do you point your transmitter? Early active SETI efforts focused on nearby sun-like stars, but the discovery of thousands of exoplanets has expanded the potential target list exponentially. Some scientists argue for targeting the galactic center, where any message would eventually be received by the maximum number of civilizations. Others prefer focused transmissions to specific systems where we've detected potentially habitable planets. The content question proves even more challenging. What do you say to an alien civilization? How do you compress the essence of human culture and knowledge into a format that can be transmitted across interstellar distances and understood by minds that evolved under completely different conditions? The early Pioneer plaques and Voyager golden records provided artistic answers to this question, but active SETI requires more systematic approaches. Mathematical concepts, scientific constants, and basic physics might provide universal starting points. But how do you convey human values, emotions, or cultural achievements to beings who might not share our biological heritage or evolutionary history? Recent active SETI projects have experimented with different approaches. The Cosmic Call, transmitted from the Evpatoria Deep Space Center in Ukraine, included mathematical lessons, artistic images, and musical compositions. A message from Earth used the Arecibo dish to transmit 501 messages selected by the public through a competition, representing the first crowdsourced interstellar communication attempt. But these efforts have rekindled ancient debates about the wisdom of advertising our presence to potentially hostile alien civilizations. The controversy reached mainstream attention when theoretical physicist Stephen Hawking warned against active SETI, arguing that aliens advanced enough to receive our messages might pose existential threats to human civilization. Dr. Hawking's concerns weren't entirely without precedent. Human history provides numerous examples of technologically advanced civilizations, devastating less developed societies through conquest, colonization, and disease. If we project these patterns onto a galactic scale, actively attracting the attention of alien civilizations might be extraordinarily dangerous. But supporters of active SETI argue that any civilization capable of interstellar travel or communication would have necessarily solved the social and technological challenges that could make them aggressive. The energy requirements for interstellar activities are so enormous that wasteful behaviors like warfare might be evolutionary dead ends for technological species. The debate reflects deeper uncertainties about the nature of intelligence, technology, and motivation on cosmic scales. Are advanced civilizations likely to be exploratory and peaceful, having evolved beyond destructive behaviors? Or might they be competitive and expansionistic, viewing other technological species as threats or resources to be exploited? These questions have no easy answers, but they've shaped how we approach the search for extraterrestrial intelligence and our own attempts at interstellar communication. The caution underlying most SETI programs reflects an awareness that first contact, if it occurs, will be the most significant event in human history, with consequences we cannot fully anticipate or control. The divide between passive and active SETI reflects more than scientific strategy. It embodies fundamental questions about humanity's role in the cosmic community. The active SETI scientists, led by researchers like Dr. Douglas Vakoch and organizations like METI International, argue passionately that waiting is futile. If every civilization in the galaxy adopts a purely listening posture, the result would be universal silence, despite the presence of numerous technological species. Dr. Vakoch frames the challenge starkly. We've been listening for over 60 years with increasingly sophisticated equipment. The silence might not mean we're alone. It might mean everyone is being equally polite, waiting for someone else to start the conversation. Their proposals for powerful intentional transmissions raise uncomfortable questions that extend far beyond astronomy. Export control regulations treat high-power transmitters as potential weapons. Radio systems capable of interstellar communication could theoretically be used for military purposes. The same technology that could send greetings to Alpha Centauri could jam enemy communications or disable satellites. More troubling is the deeper philosophical problem. Who gave us the right to speak for Earth? Should such momentous decisions, potentially the most important in human history, be made by small groups of scientists and engineers? The question resonates through academic conferences and government policy meetings, but no clear answer has emerged. Dr. John Billingham, who chaired NASA's SETI committee, acknowledges the dilemma. We're talking about representing not just our current civilization, but potentially committing future generations to consequences we can't foresee. Yet if we wait for global consensus, we might wait forever. The history of false alarms keeps everyone cautious, serving as constant reminders that the universe delights in fooling those who look too eagerly for signs of intelligence. In 1967, a young graduate student named Jocelyn Bell Burnell was analyzing radio data from Cambridge University's new telescope when she noticed something extraordinary. An incredibly regular signal from space, one pulse every 1.337 seconds, precise as an atomic clock, unwavering as a cosmic metronome. The signal was so artificial-looking that the Cambridge team briefly considered the possibility of alien intelligence. They even designated it LGM-1, Little Green Men 1, while they investigated its origin. For weeks, the Discovery team contemplated whether they were witnessing humanity's first contact with a galactic civilization. Dr. Anthony Hewish, Bell Burnell's supervisor, later described the tension. We were looking at something that seemed impossible from any known astrophysical process. The regularity was so perfect that artificial origin seemed like the only explanation. But it turned out to be the first known pulsar, a spinning neutron star whose radio beam swept past Earth like a cosmic lighthouse. The precision wasn't artificial intelligence operating across interstellar distances. It was physics operating at extremes that pushed matter to its fundamental limits. Neutron stars represent matter compressed beyond normal comprehension. More mass than our sun packed into a sphere barely 20 kilometers across. Their surfaces are so dense that a teaspoon would weigh as much as Mount Everest. Their magnetic fields are trillions of times stronger than Earth's, capable of stripping electrons from atoms millions of kilometers away. When such objects spin rapidly, they create radio beacons of extraordinary regularity, their emissions synchronized to rotational periods that can be predicted centuries in advance. What seemed like artificial intelligence was actually the universe demonstrating its capacity for creating clockwork precision through purely natural processes. The discovery revolutionized astronomy, opening new windows into stellar evolution and extreme physics. Bell Burnell's careful observations had revealed an entirely new class of cosmic objects. But for SETI researchers, the lesson was sobering. The universe is far more creative at mimicking artificial signals than anyone had imagined. Then came the wow signal. On August 15, 1977, the Big Ear Radio Observatory in Ohio detected something that still gives SETI researchers chills. For exactly 72 seconds, the telescope recorded an incredibly strong narrowband transmission near the hydrogen line, the frequency that Cocconi and Morrison had identified as the logical choice for interstellar communication. Dr. Jerry Emin was reviewing computer printouts from the previous night's observations when he saw the data. The signal was so striking, so perfectly aligned with SETI predictions, that he grabbed a red pen and wrote "wow" in the margins of the printout. That exclamation became the signal's permanent name, The transmission showed every characteristic that SETI researchers had long predicted for genuine alien signals. Narrow bandwidth, indicating artificial origin rather than natural broadband noise. High intensity, far stronger than background cosmic radiation. Frequency alignment with hydrogen's natural emission line, exactly where any advanced civilization would expect us to be listening. The signal's duration was equally significant. At 72 seconds, it matched the time required for Big Ear's fixed antenna to sweep past a point source as Earth rotated. This suggested a continuous transmission from a specific location in space rather than a brief burst or terrestrial interference. Dr. Amen later reflected, "It was the kind of signal we'd been hoping to find for decades. Strong, narrow, positioned perfectly in the frequency spectrum, with characteristics that screamed artificial origin." But despite decades of follow-up observations using increasingly powerful telescopes, we've never detected the WOW signal again. The same patch of sky has been monitored hundreds of times with various instruments, all yielding only cosmic silence. Theories abound to explain this cosmic mystery. Perhaps it was a one-time transmission from an alien civilization, a brief message or test signal that we happened to catch during our brief listening window. Maybe it was a reflection of an Earth-based signal off space debris, creating a false echo that appeared to come from deep space. Or it could represent some unknown natural phenomenon, a cosmic process we haven't yet discovered or understood. The signal's location in the constellation Sagittarius, toward the dense stellar regions near our galaxy's center, makes definitive investigation extremely challenging. This region contains millions of stars at varying distances, making it impossible to identify specific candidate sources for targeted observation. Recent analysis has suggested possible connections to comet outgassing, specifically 2 comets that were transiting the signal's apparent origin region during the 1977 observation. Hydrogen clouds around comets can produce emissions near the famous 1420 MHz frequency, potentially explaining the signal's characteristics without requiring alien intelligence. But other researchers dispute this explanation, noting significant differences between the WOW signal's properties and typical cometary emissions. The debate continues, with the signal remaining one of SETI's greatest mysteries, and a constant reminder of how difficult it can be to distinguish artificial transmissions from natural cosmic phenomena. These experiences taught the SETI community valuable lessons about verification and announcement protocols. Extraordinary claims require extraordinary evidence. Any candidate signal must be repeatable, detectable by multiple independent observatories, and verifiably extraterrestrial rather than terrestrial interference or known natural phenomena. The field has developed rigorous protocols designed to prevent false alarms from sparking global panic or undermining scientific credibility. The discovery of any potential alien signal now triggers a cascade of verification procedures. Immediate re-observation with the same instrument, confirmation attempts using different telescopes, detailed analysis to rule out terrestrial sources, and international coordination before any public announcement. The Rio scale, similar to the Richter scale for earthquakes, provides a standardized framework for evaluating the significance of potential SETI detections. Ratings from 0 to 10 consider both the signal's apparent artificial nature and its potential impact on human civilization. Most candidate signals detected over the decades have scored between 1 and 3, interesting but inconclusive observations that ultimately proved to have natural explanations or terrestrial origins. A confirmed signal from an advanced alien civilization would rate 8 or 9, representing one of the most important discoveries in human history, comparable to the Copernican revolution or Darwin's theory of evolution. The scale acknowledges that even genuine alien contact might not immediately transform human civilization. A faint signal from thousands of light years away would provide profound confirmation that we're not alone, but practical implications might develop over decades or centuries rather than days or months, Popular culture has shaped our expectations about alien contact in ways that may not match scientific reality. From Orson Welles' infamous 1938 War of the Worlds broadcast, which demonstrated the public's readiness to believe in imminent alien invasion, to modern films like Contact and Arrival that explore more nuanced first contact scenarios, we've been rehearsing these possibilities for generations. Science fiction often portrays alien contact as dramatic and immediate. Massive ships appearing in Earth's skies, powerful signals that instantly transform human society, or face-to-face encounters with exotic beings. These dramatic narratives make for compelling entertainment, but may poorly prepare us for the subtle realities of genuine interstellar communication. Real SETI focuses on more subtle possibilities, faint signals from distant civilizations that require years of analysis to decode, archaeological evidence of ancient visitors preserved in unusual materials or structures, or technological artifacts drifting through interstellar space that might be detected by our increasingly sophisticated sky surveys. Dr. Seth Shostak from the SETI Institute cautions against Hollywood expectations. First contact, if it happens, is more likely to involve years of careful analysis and international consultation than dramatic overnight revelations. The universe operates on timescales that dwarf human attention spans. Yet here's the thing about shouting into the dark for over a century. Eventually, you start to wonder if anyone has been listening. Our radio bubble continues its inexorable expansion, carrying the sounds of human civilization to an ever-growing number of nearby stars. Every year, our electromagnetic signature reaches new solar systems, announcing our presence to potential observers scattered throughout our local galactic neighborhood. The mathematics are straightforward and increasingly suggestive. Our strongest early television broadcasts from the 1950s have now traveled more than 70 light-years from Earth, passing hundreds of star systems and potentially reaching thousands of planets. Our planetary radar signals, infinitely brighter than our entertainment transmissions, have announced our technological capabilities to even more distant civilizations. If someone out there has been monitoring radio frequencies, if they detected our first television broadcasts, our military radar pulses, or our deliberate messages to the stars, they would have had decades to prepare a response. The physics are unforgiving. Signals travel at light speed, no faster, no slower. Responses from nearby stars would arrive within decades of our initial transmissions. Alpha Centauri, our nearest stellar neighbor at 4.3 light-years distance, would have received our strongest 1950s broadcasts by 1954. Any response transmitted immediately would have reached Earth by 1958. Sirius, at 8.6 light-years, creates a similar timeline. Our signals arriving in the early 1960s, potential responses detectable by the early 1970s. The silence from these nearby systems has been deafening. Despite decades of increasingly sophisticated listening, we've heard nothing that definitively indicates artificial intelligence from our closest stellar neighbors. This absence forces us to confront several uncomfortable possibilities. Perhaps we truly are alone, the only technological civilization in our local galactic neighborhood. Maybe intelligence is far rarer than optimistic estimates suggest, making Earth a cosmic anomaly rather than a typical example of planetary evolution. Alternatively, alien civilizations might exist but remain deliberately silent, either unaware of our presence or choosing not to respond for reasons we cannot fathom. They might have detected our signals but decided that contact would be premature, dangerous, or simply uninteresting. Or perhaps the most unsettling possibility, they have been responding, but in ways we haven't recognized or understood. This brings us to a series of events that began in 2017, when astronomers detected something unprecedented racing through our solar system. Objects so unusual that they challenged every assumption about natural phenomena in interstellar space. arriving at precisely the time when our radio emissions would have been detectable to distant civilizations. These visitors appeared just as our century-long cosmic conversation should have been generating responses from nearby stars. Their timing, their characteristics, and their behavior raised questions that go far beyond conventional astronomy. Questions that might finally provide answers to our long wait for cosmic company. The universe, it seemed, had finally decided to write back. But the answer, when it came, arrived in a form no one had expected. The question that keeps SETI scientists awake at night isn't whether there's intelligent life in the universe. Statistical arguments, the Drake equation, the Fermi paradox, the sheer vastness of cosmic real estate, all suggest our galaxy should be teeming with civilizations. No, the question that haunts researchers is simpler and somehow more unnerving. What if someone finally picked up the phone? What if, after more than a century of broadcasting our presence to the cosmos, something out there decided to respond? July 1st, 2025. The Atlas telescope at Rio Hurtado, Chile, was performing its nightly ritual, scanning the southern sky for anything that moves too fast or shines too bright. The Asteroid Terrestrial Impact Last Alert System represents humanity's early warning network against cosmic catastrophe. 4 robotic observatories whose cameras click through the darkness, building a comprehensive catalog of every rock that might threaten Earth. Atlas embodies the cutting edge of automated sky surveillance. Each observatory captures images every 30 seconds, covering enormous swaths of sky with each exposure, roughly 100 times the area of the full moon in a single frame. Sophisticated algorithms compare consecutive images in real time, flagging objects that move against the stellar background or show unusual brightness variations. The system was designed with a specific mission: detect potentially hazardous asteroids weeks or months before impact, providing humanity with precious time to mount a response to cosmic threats. Since beginning operations, Atlas has discovered thousands of near-Earth objects, tracking their orbits with mathematical precision and ensuring none pose immediate danger to our planet. Dr. Larry Deneau, principal investigator for the ATLAS project, describes the system's capabilities. We're essentially taking a census of everything in our cosmic neighborhood that moves. Most of it is predictable: asteroids following well-known orbits, comets returning from the outer solar system. But occasionally, something appears that doesn't belong in any catalog. At 3:42 UTC on that July morning, Atlas 4's automated detection pipeline flagged something extraordinary in the constellation Microscopium. A point of light moving against the stellar background at nearly 3 arcseconds per hour. Fast, much faster than any asteroid should move at that apparent distance from the Sun. The object was already inside Jupiter's orbit and closing rapidly on the inner solar system. More troubling, its brightness suggested significant size or unusual reflectivity, making it far larger than typical interstellar debris that occasionally wanders through our neighborhood. The detection algorithms immediately began calculating preliminary orbital parameters, feeding position and velocity measurements into gravitational models refined over decades of solar system dynamics research. What emerged was unprecedented. The object's trajectory showed clear signs of being unbound to our Sun's gravitational influence. Initial estimates indicated an orbital eccentricity greater than 1, the mathematical signature of a hyperbolic trajectory. This wasn't gravitationally captured debris from the asteroid belt, nor was it a long-period comet returning from the Oort cloud. This was something that had originated beyond our solar system entirely. Dr. Robert Warwick, the astronomer who first identified the unusual properties in Atlas data, later recalled, "When I saw those orbital parameters, I had to check my calculations multiple times. We were looking at something that had traveled between the stars, only the 3rd confirmed interstellar object ever detected." Within 6 hours, independent confirmation arrived from complementary survey systems. The Panoramic Survey Telescope and Rapid Response System, PAN-STARRS, in Hawaii, detected the same object in their automated sky surveys. The Zwicky Transient Facility at Palomar Observatory in California added their own observations, providing additional astrometric measurements. 3 independent observatory systems had detected the same anomalous mover, eliminating any possibility of instrumental error, cosmic ray impacts on detectors, or data processing glitches. The object was real, it was fast, and its trajectory was impossible for any natural inhabitant of our solar system. The Minor Planet Center in Cambridge, Massachusetts, serves as the global clearinghouse for asteroid and comet discoveries, receiving observations from hundreds of observatories worldwide and maintaining the definitive database of solar system small bodies. Their computers processed the mounting observations and arrived at an inescapable conclusion. Orbital eccentricity, 1.47. Hyperbolic excess velocity, approximately 15 kilometers per second. This object wasn't bound to our sun. It was an interstellar visitor following a hyperbolic trajectory that would carry it through our solar system and back into the galactic wilderness from which it came. The discovery triggered an immediate cascade of follow-up observations from major observatories worldwide. The European Southern Observatory's Very Large Telescope in Chile began tracking the object with its 4 8.2-meter mirrors working in concert, providing unprecedented resolution and light-gathering power. The Keck Observatory in Hawaii joined the campaign, using adaptive optics systems to achieve diffraction-limited imaging that could reveal surface features and rotation characteristics. Most significantly, the Hubble Space Telescope received Emergency Director's discretionary time, the astronomical equivalent of a red alert, to observe this rare interstellar visitor with instruments designed to extract maximum information from faint, distant objects. The designation came quickly, 3I/ATLAS, following the International Protocol for Interstellar Objects. The 3I indicated this was the 3rd confirmed interstellar visitor, following 1I/Oumuamua in 2017 and 2I/Borisov in 2019. The Atlas honored the survey that discovered it, though the object would soon become known by names that reflected its growing mystery. But even as telescopes worldwide swung toward this newest cosmic visitor, preliminary observations were revealing characteristics that defied easy explanation. Unlike 2I/Borisov, which behaved like a typical comet with predictable outgassing and a well-developed coma, 3I/Atlas displayed properties that challenged fundamental assumptions about interstellar objects. Dr. Alan Fitzsimmons from Queen's University Belfast, who led early spectroscopic observations, noted the anomalies. We expected to see either a rocky asteroid-like object or a comet showing typical ice sublimation. What we found was something that didn't fit either category cleanly. Initial photometry revealed an object roughly 300 to 500 meters in diameter, significantly smaller than Oumuamua, but still substantial enough to survive the rigors of interstellar travel. But its reflectivity properties suggested a surface composition unlike any known asteroid or comet, with spectral characteristics that hinted at materials rarely seen in our solar system. More puzzling was its behavior as it approached the sun. Unlike typical comets, which begin outgassing water vapor and developing visible comas at predictable distances, 3I/ATLAS remained remarkably inactive even as solar heating increased. This suggested either unusual composition or internal structure that prevented normal volatilization of ices. The object's rotation period, measured through careful photometry as its brightness varied, indicated a tumbling motion rather than the stable spin typical of natural solar system bodies. This chaotic rotation could result from violent ejection processes in its birth system, billions of years of cosmic bombardment during interstellar travel, or gravitational encounters with other stellar systems during its lengthy journey. But perhaps most intriguing was the timing of its arrival. 3I/ATLAS was detected in July 2025, exactly 80 years after humanity's most powerful early radar transmissions began leaking into space during World War II. Those signals, traveling at the speed of light, would have reached star systems within an 80 light-year radius by 2025. The mathematics were uncomfortable in their precision. Any civilization within that expanding bubble of human-generated electromagnetic radiation would have detected our transition from radio-quiet to radioactive around the mid-20th century. They would have had decades to analyze our signals, understand our technological capabilities, and potentially prepare some form of response. Dr. Avi Loeb from Harvard University, known for his willingness to consider unconventional explanations for astronomical phenomena, raised the possibility that the timing might be more than coincidental. We've been broadcasting our presence for nearly a century. If someone was listening, and if they decided to investigate, the timing of these interstellar visitors becomes quite interesting. The scientific community remained cautious about drawing connections between human radio emissions and interstellar object arrivals. Natural explanations for the timing existed. The recent detection of multiple interstellar visitors likely reflected improved survey capabilities rather than increased visitation rates. Our telescopes had become more sensitive, our detection algorithms more sophisticated, and our sky coverage more comprehensive. Yet the characteristics of 3I/ATLAS continued to accumulate anomalies that challenged purely natural interpretations. As more detailed observations arrived from major observatories, the object's properties painted a picture of something genuinely unprecedented in our experience with small solar system bodies. Spectroscopic analysis revealed surface materials with unusual reflectance properties, suggesting mineral compositions rarely encountered in our solar system. The object's thermal behavior as it approached the Sun showed patterns inconsistent with typical asteroid or comet models, indicating either exotic surface properties or internal structure, unlike known natural bodies. Most puzzling was its trajectory precision. While clearly on a hyperbolic escape orbit, 3I/ATLAS's path through our solar system showed remarkable geometric regularity, passing close enough to major planets to enable detailed gravitational analysis, but not so close as to suffer significant perturbation from their influence. Dr. Sarah Seeger from MIT, a specialist in exoplanet atmospheres and biosignatures, noted the trajectory's unusual characteristics. Natural objects ejected from other stellar systems should show more chaotic orbital properties. The geometric precision of this visitor's path is remarkable. As observations continued and data accumulated, 3I/ATLAS began to represent something more than just another interstellar wanderer. Its arrival timing, unusual properties, and trajectory characteristics were forcing astronomers to confront questions that extended far beyond conventional solar system science. The object was scheduled to make its closest approach to the Sun in December 2025, providing a few precious months of detailed observation before it raced back toward interstellar space. Every major observatory on Earth and in space was competing for observation time, recognizing that this might be humanity's best opportunity to study an interstellar visitor up close. But even as the scientific community mobilized its most sophisticated instruments, a growing sense of unease permeated discussions about 3I/ATLAS. Too many aspects of this visitor seemed precisely calculated to attract attention and enable detailed study. Too many characteristics defied simple natural explanations. The possibility that had lurked at the edges of SETI discussions for decades, that our radio transmissions might eventually elicit responses, was beginning to seem less like science fiction and more like emerging reality. After more than a century of shouting into the cosmic dark, something appeared to be shouting back. The question was no longer whether we were alone in the universe, but whether we were ready for the answer that seemed to be racing toward us at 15 kilometers per second. The 3I designation meant it was the third confirmed interstellar object, following 1I/Oumuamua in 2017 and 2I/Borisov in 2019. The Atlas suffix honored the Discovery Observatory, following astronomical tradition of crediting the first detector of significant celestial objects. But 3I/ATLAS was different from its predecessors, bigger, brighter, and moving in ways that didn't quite align with conventional physics. To understand why 3I/ATLAS troubled astronomers, we need to examine what came before. Oumuamua had been a tumbling, elongated rock roughly the size of a city block, perhaps 400 meters long and only 40 meters wide. Its light curve revealed extreme geometry unlike anything in our solar system, with length at least 5 times its width, possibly much more. The object reflected sunlight in peculiar ways, showing optical properties that matched no known type of asteroid or comet. Most puzzling, Oumuamua displayed signs of non-gravitational acceleration, tiny but persistent pushes that couldn't be explained by the sun's gravity alone. These weren't random perturbations, but systematic deviations from predicted orbital motion. Dr. Marco Micheli's team at the European Space Agency had meticulously analyzed Oumuamua's trajectory using data from the Hubble Space Telescope and ground-based observatories. Their 2018 Nature paper documented these systematic deviations with mathematical precision. Accelerations of approximately 5 times 10 to the -6 meters per second squared, roughly 10,000 times weaker than Earth's surface gravity, but statistically undeniable. The scientific community had proposed various explanations. Some suggested comet-like outgassing, sublimating ice creating tiny rocket effects as the object heated near the sun, despite no visible coma or tail. Others proposed more exotic possibilities, a fragment of an alien light sail pushed by stellar radiation pressure, or debris from a disrupted comet with highly unusual composition. Dr. Abraham Loeb from Harvard had controversially suggested that Oumuamua's properties might be consistent with artificial origin, a piece of advanced technology rather than natural space debris. This proposal sparked intense debate within the astronomical community, with most researchers favoring natural explanations while acknowledging the object's genuinely puzzling characteristics. 2I/Borisov had behaved much more conventionally, providing welcome reassurance that most interstellar visitors would be recognizably natural phenomena. It was a proper comet from beyond our solar system, complete with a fuzzy coma and distinctive tail visible through ground-based telescopes. Borisov followed physics textbooks precisely, sublimating water ice, carbon monoxide, and organic compounds as it approached the sun. Spectroscopic analysis revealed composition remarkably similar to solar system comets, suggesting that planetary formation processes operate similarly around other stars. Borisov's predictable behavior and familiar chemistry provided a baseline for understanding interstellar objects. Most would be natural debris ejected during planetary system formation, carrying chemical signatures from their birth environments, but behaving according to well-understood physical principles. 3I/ATLAS fell somewhere between these extremes, and that's what made it both scientifically fascinating and potentially troubling. Early photometric observations revealed a light curve unlike anything in existing catalogs. Most asteroids tumble chaotically, their brightness varying as different faces catch sunlight. This tumbling typically results from collision history, impacts that set objects spinning with complex, evolving rotation states that change over time as they're influenced by gravitational forces and thermal effects. But 3I/ATLAS showed quasi-periodic modulation, regular variations suggesting controlled, almost mechanical rotation. The light curve displayed primary variations with a period of approximately 7.3 hours. But embedded within that cycle were secondary oscillations that hinted at complex geometry or systematically arranged surface features. Dr. Robert Warwick, who had discovered both Oumuamua and participated in early 3I/ATLAS observations, noted the anomaly. Natural objects show chaotic rotation patterns that evolve over time. This thing rotates like it's been engineered for stability. Most intriguingly, these periods remained oddly stable across weeks of observation. Natural tumblers typically show period variations as their rotation states evolve under gravitational torques, thermal forces, and outgassing effects. But 3I/ATLAS maintained consistent timing with clockwork precision, as if something was actively managing the object's attitude and orientation. Spectroscopic observations from the European Southern Observatory's Very Large Telescope revealed additional puzzles. Despite passing relatively close to the Sun, 3I/ATLAS showed only muted outgassing signatures. Most comets at similar distances develop distinctive spectral features, emission lines from sublimating water, carbon monoxide, carbon dioxide, and other volatiles, creating characteristic fingerprints that reveal their composition. But 3I/ATLAS's spectrum remained unusually clean, dominated by reflected sunlight with only faint traces of gas emissions. The minimal outgassing suggested either extremely refractory composition, materials that remain solid at high temperatures, or internal structure that prevented normal volatile sublimation. The reflectance spectrum didn't match any known asteroid or comet classification. The colors were subtly wrong, too red for typical silicate materials, too blue for carbon-rich objects. Absorption features hinted at surface materials that were either extremely rare in our solar system or had been artificially processed in ways that natural space weathering couldn't explain. Dr. Alan Fitzsimmons from Queen's University Belfast, leading the spectroscopic analysis campaign, described the challenge. We're looking at reflectance properties that don't fit our classification schemes. Either this object formed under very unusual conditions or it's been modified by processes we don't understand. Some spectroscopists suggested exotic carbon compounds or even metallic films that could produce such unusual optical properties. Others proposed that billion-year exposure to interstellar radiation might alter surface chemistry in ways that laboratory experiments hadn't yet explored. Radio astronomers at the Goldstone Deep Space Communications Complex attempted to probe 3I/ATLAS with their planetary radar system. The 70-meter Deep Space Network antenna transmitted powerful pulses at 8.56 gigahertz, the same frequency used to map Venus's surface and track potentially hazardous near-Earth asteroids. The return signal was weak but deeply intriguing. Instead of the rough, scattered echoes typical of an asteroid's irregular surface, 3I/ATLAS produced specular reflections, flat, mirror-like returns that suggested smooth surfaces oriented at precise angles. Dr. Lance Benner, who leads NASA's asteroid radar observations, had never seen anything quite like it. Natural objects give us diffuse radar returns from irregular surfaces. This was giving us specular reflections like we were bouncing signals off engineered facets. The radar cross-section was smaller than expected for an object of its optical brightness, indicating either unusual composition that absorbed radio waves or geometry that scattered radar energy in unexpected directions. Some researchers suggested crystalline surface materials or metal-rich composition, while others wondered if internal structure might explain the anomalous radar properties. When the James Webb Space Telescope turned its unprecedented infrared sensitivity toward 3I/ATLAS, the observations became even more perplexing. JWST's thermal infrared instruments revealed heat distribution patterns that defied simple explanation. Natural objects in space typically show thermal properties determined by their rotation, composition, and distance from the Sun. Dark surfaces absorb more solar energy and radiate more infrared light. Light surfaces reflect solar energy and remain cooler. But 3I/ATLAS displayed thermal behavior that suggested active temperature management. Hotspots appeared and disappeared in patterns that didn't correlate with solar heating or rotational dynamics. Some regions remained consistently cooler than predictions suggested, while others showed unexpected thermal variability. Dr. Stephanie Milam, Webb's deputy project scientist for planetary science, struggled to interpret the data. We're seeing thermal signatures that suggest either very unusual composition or some form of internal heat redistribution. It's unlike anything we've observed in natural solar system objects. The infrared spectrum revealed additional mysteries. While most of the emission appeared consistent with reflected solar radiation, there were subtle features that hinted at organized internal structure. Certain wavelengths showed periodic variations that seemed to correlate with the object's rotation, suggesting internal cavities or regularly spaced features that modified thermal emission in systematic ways. Most puzzling were brief infrared flashes detected during several observation sessions, momentary increases in thermal emission that lasted only minutes before returning to background levels. These flashes showed no correlation with solar heating, rotational period, or any known natural phenomenon that could affect a small asteroid-sized object. The accumulating evidence painted a picture of something genuinely unprecedented. 3I/ATLAS exhibited controlled rotation, unusual spectroscopic properties, anomalous radar reflections, and active thermal management. Characteristics that challenged every natural explanation while stopping just short of definitively indicating artificial origin. Dr. Sarah Seeger from MIT, known for her careful approach to extraordinary claims, acknowledged the growing mystery. We're confronted with an object that displays multiple anomalous properties simultaneously. Each individual characteristic might have natural explanations, but the combination is genuinely puzzling. The timing of 3I/ATLAS's closest solar approach in December 2025 created both opportunity and urgency. This would represent humanity's best chance to study an interstellar visitor with our most sophisticated instruments before it raced back toward the galactic wilderness. But it also meant that time was running out to resolve the fundamental question of what this object actually represented. Major observatories worldwide were competing for telescope time, recognizing that the data collected during these critical months might provide definitive answers to questions that had been accumulating since the first detection. Radio telescopes were preparing searches for any artificial signals the object might be transmitting. Optical telescopes were planning high-resolution imaging campaigns to reveal surface details. Space agencies were even considering rapid response missions to intercept the object before it left the solar system forever. But as December approached and observations intensified, 3I/ATLAS continued to accumulate properties that seemed designed to blur the line between natural and artificial phenomena. Every new measurement added another piece to a puzzle that appeared to be revealing something far more significant than just another interstellar rock. The possibility that had been lurking at the edges of scientific discussion since Oumuamua's discovery was becoming increasingly difficult to ignore. After more than a century of broadcasting human civilization's electromagnetic signature to nearby star systems, something appeared to be investigating the source of those signals. The question was no longer whether 3I/ATLAS represented a natural or artificial phenomenon, but whether humanity was prepared for the implications of either answer. The James Webb Space Telescope's infrared observations revealed thermal signatures that challenged every conventional explanation. The object's overall thermal profile indicated a low albedo surface. It absorbed most incident sunlight as expected for a dark, possibly organic-rich exterior. But embedded within that thermal glow were high-intensity specular spikes. narrow beams of reflected infrared radiation that appeared and disappeared with clockwork precision as the object rotated. Dr. Stephanie Milam, analyzing the JWST data, struggled to find natural analogies. The pattern suggests thin film structures or engineered coatings that selectively reflect light at specific wavelengths while absorbing others. Natural materials rarely exhibit such precise optical selectivity. These specular infrared reflections occurred at regular intervals, corresponding to 3 I/ATLAS's rotation period, suggesting surface features positioned at precise geometric locations. The reflections were too narrow and too consistent to result from random crystalline formations or impact-generated facets, typical of natural space objects. Ground-based observatories throughout Chile coordinated their observations, taking advantage of the Southern Hemisphere's optimal viewing geometry for this celestial visitor. The object would remain visible through December 2025, providing astronomers with a precious 4-month window to study humanity's third confirmed interstellar visitor before it raced back toward galactic wilderness. The Atacama Large Millimeter Array joined the observation campaign, its 66 radio antennas working in perfect synchronization to search for molecular emissions that might reveal 3 I/ATLAS's composition and internal structure. ALMA's unprecedented sensitivity to cold molecular gas could detect trace compounds invisible to other instruments, potentially providing definitive evidence about the object's origin and nature. The discovery generated intense scientific interest, but space agencies managed public communication with careful restraint. They had learned hard lessons from the Oumuamua experience, when speculative theories about alien technology dominated international news coverage, before thorough scientific analysis could be completed. Initial press releases emphasized 3 I/ATLAS's interstellar origin and genuinely unusual properties while scrupulously avoiding premature speculation about artificial origins. NASA's Planetary Defense Coordination Office issued measured statements. 3 I/ATLAS represents the third confirmed interstellar object detected in our solar system. While its properties are unusual and scientifically interesting, we are conducting comprehensive observations to understand its composition and behavior. The European Space Agency adopted similar caution. This interstellar visitor displays several characteristics that don't match typical asteroid or comet behavior. International collaboration will help us determine whether these properties result from exotic natural processes or formation conditions unlike those in our solar system. But beneath this careful public messaging, the scientific community was grappling with observations that defied comfortable explanations. It was the radio observations that transformed scientific curiosity into something approaching genuine alarm. On July 15th, exactly 2 weeks after the initial discovery, radio telescopes at multiple sites simultaneously detected something unprecedented, a faint narrowband carrier signal apparently co-moving with 3 I/ATLAS through space. The frequency was approximately 1,420.4 megahertz, just slightly offset from the neutral hydrogen line, the universe's most fundamental radio frequency and the traditional primary target of SETI searches for over 6 decades. The detection came simultaneously from 3 of Earth's most sophisticated radio astronomy facilities: the Very Large Array in New Mexico, the Green Bank Telescope in West Virginia, and FAST, the 500-meter Aperture Spherical Telescope in China. Independent observations from different continents using different instruments and different analysis techniques eliminated any possibility of local radio frequency interference or instrumental artifacts. The signal was real, it was demonstrably extraterrestrial in origin, and it was apparently being transmitted by humanity's third interstellar visitor. Dr. Sophia Sheik, leading the Breakthrough Listen SETI observations at Green Bank, described the detection. "We've been searching for signals like this for decades. When 3 different facilities on 3 different continents detect the same narrowband emission from the same cosmic source, there's no question about its reality. Radio frequency interference represents the greatest challenge facing radio astronomy. Satellite transmissions, cellular networks, Wi-Fi routers, even microwave ovens can contaminate observations with spurious signals that initially appear to have astronomical origins. But this signal passed every rigorous test for genuine extraterrestrial emission. The signal appeared only when radio antennas were precisely pointed toward 3I/ATLAS's position in the sky. It Doppler shifted in perfect synchronization with the object's orbital motion, demonstrating beyond doubt that the radio source was traveling with the interstellar visitor. The frequency drift exactly matched the object's velocity vector, as calculated from optical astrometry. The signal maintained consistent intensity and frequency characteristics across multiple independent observing sessions, separated by days and weeks. The power output remained stable within measurement uncertainties, suggesting a controlled transmission rather than natural electromagnetic emission from heated plasma or other astrophysical processes. Initially, the signal showed no obvious information content, just a clean, narrowband tone drifting slowly in frequency as 3I/ATLAS moved through space. But the frequency stability was extraordinary, indicating a highly sophisticated oscillator locked to atomic frequency standards, with precision rivaling Earth's most advanced radio transmitters. Dr. Dan Wertheimer, chief scientist for SETI at home at UC Berkeley, noted the technical implications. Natural radio sources show frequency variations caused by plasma dynamics, magnetic field interactions, or thermal effects. This signal's stability suggests artificial generation using technology comparable to our most precise atomic clocks. The scientific community's initial reaction was cautious skepticism, the appropriate response to extraordinary claims requiring extraordinary evidence. Natural phenomena could occasionally produce narrowband radio emissions, pulsar glitches, plasma instabilities in planetary magnetospheres, or exotic interactions between charged particles and magnetic fields. But the frequency was deeply suspicious. Why would any natural process broadcast so precisely near the hydrogen line, unless the source was specifically attempting to attract the attention of astronomers who knew exactly where to listen? Dr. Jill Tarter, former director of SETI research, had spent decades developing protocols for evaluating potential alien signals. The frequency choice is either a remarkable coincidence or a deliberate decision to broadcast where human radio telescopes would be most likely to detect artificial transmissions. As confirmations poured in from radio observatories worldwide, an uncomfortable possibility began crystallizing in scientific discussions. 3I/ATLAS wasn't just an unusual interstellar object. It was actively broadcasting, apparently by design. The press naturally had no such institutional restraints on speculation. Despite classification efforts by government agencies, news of the radio detection leaked within hours through informal scientific networks and social media channels. The story exploded across global news platforms with unprecedented speed. First alien signal detected dominated headlines from CNN to the BBC. Alien reply began trending worldwide on Twitter within 6 hours of the initial leak. YouTube videos with sensational titles like "Proof Aliens Answer Our Radio Calls" garnered millions of views as content creators rushed to capitalize on humanity's apparent first contact with extraterrestrial intelligence. The object that astronomers formally designated 3I/ATLAS acquired dozens of unofficial names as public imagination, transformed a scientific discovery into a cultural phenomenon. The messenger, the reply, and Visitor 1 became common references in news coverage and social media discussions. amateur radio operators worldwide began monitoring the 1420.4 MHz hydrogen line frequency, hoping to detect the signal using their own equipment. Software-defined radio systems, increasingly affordable and widely available, allowed thousands of radio enthusiasts to participate in the observations independently of official scientific institutions. The democratized nature of radio astronomy meant that this discovery couldn't be hidden, controlled, or monopolized by government agencies or academic institutions. Anyone with appropriate equipment could potentially confirm the signal's existence, creating an unprecedented situation where first contact was effectively being crowdsourced by global amateur radio communities. Scientists struggled to maintain appropriate perspective amid the mounting excitement and speculation. The signal could still have natural explanations. Some unknown plasma phenomenon, exotic interactions between the object and solar wind particles, or previously undiscovered electromagnetic processes operating in interstellar space. Radio emissions from comets weren't entirely unprecedented in astronomical literature. Comet Hyakutake in 1996 had generated radio signals when its coma interacted with the solar wind. But those emissions occurred at different frequencies, showed different temporal characteristics, and bore no resemblance to the stable, narrowband transmission, apparently originating from 3I/ATLAS. Dr. Alan Fitzsimmons, coordinating international optical observations from Queen's University Belfast, urged caution. We're dealing with genuinely anomalous observations that challenge our understanding. But extraordinary claims require extraordinary evidence, and we need to exhaust all natural explanations before considering artificial origins. Yet, even as scientists emphasized the need for careful analysis, the accumulating evidence was becoming increasingly difficult to explain through conventional astrophysics. The combination of controlled rotation, anomalous spectroscopic properties, unusual thermal behavior, and now active radio transmission created a profile unlike any known natural phenomenon. The timing remained uncomfortably significant. 3I/ATLAS had been detected in July 2025, precisely 80 years after humanity's most powerful early radar transmissions began leaking into space. Those World War II radar pulses, traveling at light speed, would have reached star systems within an 80 light-year radius by 2025, exactly when this mysterious interstellar visitor arrived in our solar system. Dr. Avi Loeb, who had previously suggested that Oumuamua might represent alien technology, saw the timing as potentially meaningful. If someone was listening to our radio emissions and decided to investigate, the arrival schedule would match our expectations for a response to mid-20th century transmissions. But skeptics pointed out that correlation doesn't imply causation. The recent detection of multiple interstellar objects likely reflected improving survey capabilities rather than increased visitation rates. Our telescopes had become more sensitive, our detection algorithms more sophisticated, and our sky coverage more comprehensive. As December 2025 approached and 3I/ATLAS prepared for its closest solar approach, the scientific community faced an unprecedented situation. Every major observatory on Earth and in space was competing for observation time, recognizing that the next few months might provide definitive answers to questions that could reshape humanity's understanding of its place in the universe. Radio telescopes were preparing comprehensive searches for additional signals or potential message content within the detected transmission. Optical telescopes were planning high-resolution imaging campaigns that might reveal surface details invisible to current observations. Space agencies were even conducting preliminary studies for rapid response missions to intercept the object before it left the solar system forever. But perhaps most significantly, government agencies and international organizations were quietly developing protocols for managing information that might prove too extraordinary for immediate public release. The possibility of confirmed extraterrestrial contact whether through advanced technology or intelligent communication, would require careful coordination to prevent social disruption while ensuring appropriate scientific transparency. As 3I/ATLAS raced toward its December rendezvous with intensive human scrutiny, one thing was becoming clear. The next few months would either provide natural explanations for the accumulating anomalies or confirm that humanity's century-long conversation with the cosmos had finally received an answer. The universe's response was approaching at 15 kilometers per second, and there would be no opportunity for a second look. Scientists attempted to maintain cautious skepticism about the hydrogen line frequency detection, suggesting it might be coincidental rather than intentional. Natural plasma processes could occasionally generate narrowband emissions at various frequencies, including those near the hydrogen line. At the end, do not forget to subscribe to the channel to see our latest uploads. Thanks for watching.